And here to lead our discussion is the Aviation Week Executive Editor for Technology. And he's a Hydrogen Aviation Summit stalwart, I'm pleased to say. So we're doing something hopefully right, Graham, because you keep coming back. And Graham will not be a stranger to most of you. He's a leading commentator on aviation technology. He's been an aerospace journalist for, I think, more than 40 years. And also he makes a regular appearance on Aviation Week's excellent Check 6 podcast, as well, obviously, in the magazine's pages. So Graham, thank you for joining us, and please introduce the panel and our guest speakers, please.
I will, and thank you for inviting me again. I'm Graham Warwick with Aviation Week magazine, and I've been writing about electric aircraft for probably more than 15 years now, when they first sort of started in some of the NASA work and then something, but we've seen it become a reality. And one of the things that's interesting to me is that the technology got its start by taking the technology that was in the automotive world, the EV technology, the motors, the batteries, and adapting them to aircraft. So that's what we've seen, how we've seen this start. It's the same with fuel cells. The basic technology that's initially being applied has come out of the heavy vehicle market, that sort of thing. But what you are also seeing is that as soon as we get aeronautical engineering applied to a technology, you very quickly start to see quite dramatic improvements in performance, reliability, safety, reductions in weight, increases in power density, much greater redundancy and things like that. So it's really interesting to see how fast just the electric motor, electric drive piece of this equation has moved. Forget the batteries, forget the fuel cells, just look at the actual drivetrain. Doesn't matter where the energy comes from. Look at how that drivetrain is rapidly evolving. So we're in a situation now where, and we've got this example on our panel today. We've got the now, which is how do we certify an electric powertrain? Probably using technology that may have started in the automotive world, but has been adapted and improved for aerospace. We've got the next, which is, okay, now we really start applying aerospace engineering to electric machines, and we get much, much higher power levels. We get much greater integration of all the pieces that are separate in a car now becomes an integrated whole, and you get much more complex and clever approaches to thermal management, getting rid of the electric engines are very efficient, but when they get powerful, they still put out lots of heat. So you've got to get rid of that heat in a way that doesn't generate too much drag and weight. So you're seeing all of this expertise, this aerospace experience being applied to this technology. And then our third panelist comes in with the viewpoint of, we may be getting started with retrofitting existing aircraft to get the market going, but really this technology comes into its own when we can apply it to a clean sheet airplane. So you start to see aircraft emerge that are designed around electric propulsion. So you're starting to see, and they look different to the airplanes we've designed in the past because the trades work out differently. The traditional range equation isn't quite as applicable to an electric aircraft as it is to a turbine aircraft. You've got this ability to have different energy sources. The electrons can come from different places. So you start to see these airplanes that are coming along that are looking different. So we've got those three today. So we're going to start with Paul Murphy. Paul is the Chief Technology Officer for Propulsion with our host, ZeroAvia. Previously, he was VP engineering for the electric engine at Archer Aviation, the eVTOL air taxi developer. Before that, fascinatingly, he was VP product design at Koenigsegg, which is a Swedish hypercar manufacturer. And that's the bit of his story I'd love to know more about. And then he was with, like a lot of those people in this industry, he was with Tesla, who really got us started on this journey so many years ago. Our second speaker is Jeff Engler. Jeff is the next piece of this panel. He's already showing how far we can move electric machine technology once we apply that engineering discipline I talked about. He's the CEO of Wright Electric, which was founded in 2016 in the US to develop high power electric propulsion systems. He's a serial entrepreneur, probably is the best way to describe him. And his experience has included the health industry, banking, but now he's fully focused on aviation. At least I hope he is, because he's doing some pretty amazing stuff. And our third speaker is George Alafinov. George is the co-founder and CEO of JEKTA Aviation, which is a Swiss startup that is developing an amphibian, a 19-seat regional amphibian, true commercial aircraft, clean sheet design, based around distributed electric propulsion and hydrogen fuel cells. So he's bringing all this technology together in a brand new aircraft design. So I'm going to kick off first with Paul, move to Jeff, then to George. So Paul, tell us about where you are with ZeroAvia at the moment.
Yeah, thanks so much, Graham. Just taking myself off mute. It's a pleasure to be here with you all. So right now, we're in a very exciting time with ZeroAvia, and we are on the cusp of certification with our electric engine here that will really kick us off into our longer journey as we really scale up into the industry to develop hydrogen electrification throughout the industry. So right now, you asked where we're at. We are in the middle of our tests for our what we call ZA 600 program. And this will be the first offering that we really move through with the FAA to kind of open up this door to the rest of the industry as we go through certification. So there's this big wall that everybody's up against right now to move through certification. And as we go through that, it will really bring everyone to the same page through the regulation.
Val, CEO of ZeroAvia, yesterday mentioned that you're doing certification with the FAA and CAA. It's usually you work with one regulator and validate with another, but I understand that you're working simultaneously with both regulators. Could you kind of walk us through that?
Yeah, it's a great question. So right now, we want to leverage the strengths of the industry and the global market. So right now, we see the US and the FAA as being a little bit further along in the story with eVTOLs and some of the electrification that's going on in the aviation world. But it is focused primarily on battery technology. We haven't really tapped too much into some of the other power sources. And what we want to do is capitalize on that with our electric engine, because we're agnostic to how the electrons flow, like you mentioned before. We could have multiple power sources. And so we're going to certify with the FAA our electric powertrain first, the electric engine. And that's what we're planning for this year. So then after that, we're working through other regulators for the hydrogen store, and we're going to piece all these together to actually bring this to the aircraft level. So this is why we're working both regulators in we'll say in concert together, so that we can actually speed up the process versus putting a lot of pressure on one regulator to do the whole system, because these are multiple systems, some of them more complex than others, and we want to focus the regulator onto what's key and see if we can, we'll say, lighten the lift there.
Thank you. So I'll move to Jeff now. I'm going to come back. I want to talk to you about vertical integration later and things like that. But Jeff, you're really pushing the boundary here. So give us some background on what Wright is doing.
Absolutely. Thanks, Graham, and thanks to the ZeroAvia team for inviting me. I'm come from Wright Electric. We build motors and batteries to enable large 100+ passenger airplanes to become hybrid electric and eventually fully electric. We do a lot of work in the U.S. with government agencies, including NASA, the U.S. Department of Energy, the Department of Defense, and the FAA. And actually, this timing is great because yesterday we announced that our second version of our megawatt electric propulsion unit has begun testing. So it's a 2.5 megawatt machine designed for ducted fan and propeller-based applications with industry-leading power and power density.
So you've in effect, Wright has come out of nowhere and really taken electric machine technology for aerospace, quite a long distance from from those initial machines that we saw on some of the early prototypes. Do you have, now it's interesting that you're working on batteries and other things like that. Is there any concern that you have that you're going to be early to market, you're going to early to need, you're going to get this technology developed, but the market or the OEMs, because we're seeing delays all the time in the OEMs and things like that. Are you concerned that you could be early to need, or do you think that the technology has other applications that you can take advantage of? I know you're doing ground power type of things like that. Could you just address that?
Yeah, absolutely. So we earlier this year launched an effort to look at the C-130 cargo aircraft for electrification, both as a hybrid electric platform to be used, let's say, for the commercial cargo industry, but then also for the Department of Defense to add electrical power, continuous electrical power at high altitude. And what we found is interest in both of those areas. And so maybe for a clean sheet 150 passenger airplane, sure, we're early for that. That's not going to get to market, let's say until the mid 2030s. But if you look at the demand for retrofitted aircraft at the narrow body class, the C-130 has the max takeoff weight, for example, of a 737. So it's already in that category. And we're looking at potential certification as soon as the end of this decade. And when we look at our own certification platform and timeline for our propulsion unit, that's looking at certification towards the end of this decade as well. And so, yes, it's early from the perspective of a clean sheet designed from scratch, large regional jet or narrow body class airplane that'll enter service in the 2035 timeframe. But in terms of a retrofitted platform where there's immediate demand today, the C-130, for example, where there's both immediate demand on the commercial cargo and on the Department of Defense side, I think that's on track, and I'm happy we are where we are given the amount of demand that we've seen.
And it's a good point, because there's this continually increasing demand for onboard power on a lot of these military platforms. They're putting sensors and systems on these vehicles that demand huge amounts of power. There's also this, which I think is fascinating, the ability for the aircraft to be a generator when it arrives wherever it deploys to. We're looking at these aircraft being mobile power stations in essence, in some situations. So it's a very different market with some interesting angles to it. So George, over to you. Now you're really bringing already, I think it's just amazing in the few short years we've been doing electric aviation, you're already bringing so many different pieces together. The distributed electric propulsion, the hydrogen fuel cell, the operating from water, which is this whole idea of get away from congested airports, get away from airports that are not convenient, get away and get into places that can't, others can't get into. So you're really bringing all this together in one idea. So give us a bit of background on JEKTA.
Yeah, thank you very much. It's a pleasure to be here. With those that are unfamiliar with our product, we're developing a 19-passenger unpressurized amphibian aircraft that is able to seamlessly connect existing airports and water for coastal and island nations, providing an opportunity for a quick setup of last-mile operations with minimum investment and minimum ecological impact. Water is nature's best gift and primary source of life on the planet. Water is also a source for production of hydrogen through electrolysis. And paired with solar panels, it creates an ability to produce fuel completely off-grid. This technology is actually developed by ZeroAvia, among others. And it is particularly crucial for island nations where land is scarce and fuel delivery is challenging and costly. Therefore, we want to use the gift of water as both runway and energy source for our aircraft. Actually, it opens up enormous opportunity for an Asian market, as mentioned yesterday by Professor Rob Miller of Cambridge University. Millions of passengers in Asia will be taking their first flight soon, and we would like it to be on our hydrogen-powered aircraft, taking them from water to the international airport or other regional destination.
So, obviously, the hydrogen from the water is a natural, and obviously it avoids this thing about having to electrify the shore side of things, which is beginning for electric boats, but is a big barrier to electrification. Yeah. As he talked to Harbour Air in Vancouver, they've had some issues trying to put charging into some of these, these small harbours that they serve into. It's not necessarily just a straight getting the power to the jetty and all that stuff. So is electric propulsion natural for the water environment, or is it the distributed nature of your electric that really makes it work?
No, what makes it work is, first of all, that the world is changing and we need to have electric propulsion system on our aircraft simply for several reasons. A, it allows us for flexibility of design. We're not shoehorned into the available engines that are today out there in the market. Some of them are 60, 70 years old in design, albeit modernized several times, but still very, very costly. Very, very inefficient, and just huge on maintenance costs. We want to use distributed propulsion system to have a blow lift effect over the wing in order to take off the water or land as quickly as possible. For any aircraft, land or water is an enemy rather than a friend, especially when it comes to energy consumption. So we want to have an aircraft that has a very short takeoff and landing capability in order to provide for opportunity for operations in limited environments such as rivers and lakes lakes of Scotland, for example, or little bays, et cetera, et cetera. And this is only available with distributed propulsion system in our case, because we also need to have a very large wing to carry all those passengers and all that cargo. This is where we're looking into the electric engines themselves. And certainly what we've now discussed and yesterday's in the panel, there's a lot of other advantages for electric engines, and Jeffrey surely can tell us more about it in terms of maintenance costs, in terms of lack of moving parts, in terms of possibilities, and last but not least, huge life cycle of electric engines and extended overhaul periods. So these are all the advantages that allow us to bring the OpEx of the aircraft. And in our case, when we're looking at the emerging markets, such as the Middle East and Asia, it's one of the most important characteristics. It's not the capital that's required to purchase the aircraft, because now we're moving to a little bit different paradigm of business where you have leasing companies and operators, but it's the actual operating costs that are more important, because this allows for selling tickets to a wide range of passengers. And if we're talking about the economies of scale, if we're talking about Asia, it's several billion people. If you're able to capture 5% of the middle class in Asia, that's millions and millions of passengers. And our approach is, on top of that, not only the OpEx of the aircraft, but the investment in building regional airports is not necessary, because you can already use all the water that has been given to you. And in fact, it's nothing new. All global aviation before the World War II was flying from the water. Yeah. So we actually want to go back in history and just using new materials, new electric propulsion, and the fuel cell by ZeroAvia for all those advantages to build a tool, an instrument to bring back the aviation from the water, because we believe it's a huge opportunity to capture that market.
So Paul, I wanted to come back to you, and so ZeroAvia started out, it took automotive technology and built its prototypes, but then it decided to bring that vertically integrate, bring it in-house, even though the company you were working with actually spun off a aerospace-focused motor developer. What was your reasoning behind the vertical integration? And can you address both the advantages to you, but what the challenges are if you take that on, that vertical, that integration?
Sure. Yeah, this is actually one of my favorite topics, coming from my past. So vertical integration is, we'll say, the holy grail of how to move technology forward. And how you actually move an industry or create a new industry. From some of my past lives, vertical integration was key because people didn't believe or people didn't want to support. And so you had to vertically integrate. But people quickly learned that this brought more control, this reduced cost, this, sped up your timeline. All of these are benefits of vertical integration. And so when you put the business case together, all of that you have to really put into the game is more sweat, more elbow grease, more strength. And this can be a challenge because you have to bring the right talent. But the benefits far outweigh anything else that you're going to see in the industry. And this is actually I would say one of the challenges with the existing establishment or the existing established industry in any industry is when you see people removing vertical integration and spreading out, it's almost directly related to technology advancement, because people don't have the flexibility or the ability to move quickly into the next phase. And so I think as you see, we'll say, this new generation in aviation pull back into vertical integration in many areas, you're going to see the technology start to improve and ramp quite rapidly.
But don't you commit the company to decades of investment to stay ahead of people like Wright that just focus on developing electric engines? If you're vertically integrated, you've got to stay at the leading edge of the technology. Isn't that a huge investment commitment?
Well, it could be, depending on how you look at it. But what we see in the aerospace industry, we'll say compared or contrasted with the automotive industry, is lower volumes. Now, it's still higher volumes for the aerospace industry, but when you have lower volumes, you create more flexibility and we'll say a less or lower need for investment, and you can change faster. So some of the things that maybe don't work in the automotive space work quite nicely in the aerospace industry. I mean, additive manufacturing is just a quick example where, you're never going to get the speed in additive manufacturing for the automotive industry at any volume. However, you can use this all day long in the aerospace industry under the right regulation and certifications. So these are just examples where we can shift we'll say, investment that we might think of traditionally as being really large into something that's more flexible. And once you have that flexibility, I would say vertical integration brings much more flexibility, even from an investment perspective.
So Jeff, so you had to build a company up to develop a large highly integrated electric machine. And you've now taken this step forward into also developing these high energy density batteries and other things like that. Can you give us your view on that need or the benefits and also the challenges of bringing so much in onto yourself of what you have to do to get to market?
Yeah, absolutely. I mean, it's a very daunting challenge, no matter what. Looking at the motors, if you just look at the power density of our machine, for example, so that's the power to weight ratio, kilowatts per kilogram. A typical industrial motor maybe might have 0.5 or 1 kilowatts per kilogram. Some motors you might buy today for aerospace applications might have 3 or 4 kilowatts per kilogram. Our first motor, was targeting 10 kilowatts per kilogram, and this one is targeting 18 to 20. So huge advances, and it's very difficult at each level in order to get there. And that's the same thing we're trying to do for our batteries as well. A typical lithium-ion battery might be 200 watt hours per kilogram, and we're trying to achieve north of 600, 700, 800 watt hours per kilogram, which, in a sense is similar to what ZeroAvia is doing just on the fuel cell side. And I think, Paul said it earlier, it's daunting when you think about the challenges. But then on the other hand, in terms of the opportunities, flying is so bad for the environment, and it leads to so much noise, so much community noise. In the United States, for example, 70% of people fly 0 or 1 time per year. And yet you have millions of people living in the glide path of an airport, and they're hearing the noise from airplanes taking off and landing. Not to mention, obviously, the carbon footprint, which you don't see as much, but impacts things. And then there's going to be a large rise in the Asia Pacific region over the next 20 years. So you should see even more impact. And so, yeah, of course, on the one hand, when you think about the technology that's going to be needed, it's difficult, but the opportunity to really make an impact in millions or billions of people worldwide is, I think, why people show up, as employees at ZeroAvia and JEKTA and Wright every single day.
George, you're coming in as a new OEM. The industry's been running a little while now. You're coming in. A lot of the vertical integration that we see was attributed at the beginning of this industry to a lack of a supply base. There was nobody out there doing this, so we needed to bring it in-house. You're an OEM. You're out there looking at what the market is offering you. What's your sense of where the market is? Do you feel confident that systems with the performance and the costs and everything that you need are becoming available within this industry?
Well, as a new OEM, but with a team that has more than 2 decades of experience building aircraft, we've always built aircraft working with the suppliers. So an aircraft is essentially an assemblage, an assembly of different parts that are supplied by our suppliers. Personally, I believe we, as a Part 23 aircraft, we don't have the resources and the time to develop certain components ourselves. More so, we don't have the resources to certify that, because if we stuck on certifying, for example, fuel cell made by ZeroAvia, then we'll need a whole team working for years to do that instead of developing the aircraft itself. So we actually rely on companies like the Wright Electric for our engines, for example, which we're not partnering, but as an example, or ZeroAvia to provide our fuel cells, propellers, avionics, et cetera, by other suppliers, and assembling them together into the vision of the aircraft that we have. When it comes to today's field of suppliers, there's a very wide plethora of suppliers for general aviation and for Part 23 aircraft. The real challenge here and the big X factor is, and the question mark is, of course, the fuel cell by ZeroAvia and the electric motors. And this is where we're looking for the best possible supplier and the one that we have the most confidence in. And we have chosen, out of many we have talked to, we've chosen ZeroAvia because we believe they have the necessary capacity and resources, not only to develop technology, but also certify technology. And this because this is the biggest problem today in aviation, is the cost and time it's required to certify, especially new technologies.
So Jeff, I'm going to take one of the questions from the audience here. You moved into the batteries, and I get the sense is that you see these very combined. If you're going to find a market for your 2 megawatt motors or your multi-megawatt motors, you also need to have some control over making sure the batteries are available that could make those motors work. So the question relates to like the C-130 is a retrofit. There are some, it talks about you can't really put, where do you put the batteries in the C-130? In a clean sheet airplane, you can put the batteries in the wing, you can get a snowball effect of the weight reduction and load relief. And what do you trade in a clean sheet? So how do you weigh up range limited retrofits versus clean sheet for battery aircraft? Can you still make a viable business case for a retrofitted C-130, given the limited constraints?
So that's a great question. What I'm going to do after I speak is I'm just going to put in the chat window a link to some papers that have been written about this. NASA wrote a paper over the summer in July of 2024 specifically about the C-130 as a retrofit candidate. And it's a fascinating paper written out of NASA Glenn and NASA Ames, and they have some follow-up papers coming out at SciTech in January that look at the cost economics and a little bit more details. But the quick answer is, so the first question is, where do you put the batteries? Their idea is to put them in pods along the wings, because then you don't give up cargo carrying capacity from a volumetric perspective. The second point, though, is what are the range limitations? So what they get to is you don't give up volume, you do give up some payload, you give up some range as well. So the airplane could go, let's say, 2,000 miles. Now it can only go about 600 miles, but it turns out 600 miles is about 75% of the range of a typical cargo airline. So you're not actually giving that much in a practical sense. But what's mind-blowing is you can get up to 25 to 40+% fuel burn reduction. And so why does that matter? So again, 25 to I think 44% fuel burn reduction. And the reason that's important is that the business model of an airline is that they have pretty low profit margins. So they might have profit margins as low as 5 or 10%. And fuel is one of their single largest costs. Fuel can be up to 30% of their costs. So if you take an industry, and the cargo industry is even more so. So if you take an industry like the cargo airline industry that has low profit margins and very high fuel costs, and you can reduce those fuel costs by as much as 20, 30, or 40%, you have a meaningful opportunity to change the cost economics of the cargo industry. And then you could say, okay, fine, it's just the cargo industry. But you know what? That's a great start because, from a risk perspective, it's really nice to think about starting with a platform where you're not carrying paying passengers, you're mostly just carrying cargo. And it's a hybrid electric design. So you do still have some thermal engines. It's basically a 2x2 system, 2 thermal engines, 2 electric engines. And then again, you're putting the batteries in the cargo pods. So what I'm going to do after this is I'm going to put some links into the chat window. And if anybody wants to follow up afterwards, we wrote a white paper on this and actually ended up getting picked up by Aviation Week as well. So Graham, you wrote about it as well. So happy to follow up afterwards about it, but I'll just put some of these links into the chat window for folks.
Thank you. So Paul, George mentioned this. There's a lot of talk about the maintenance benefits of electric motors, the long TBO for start off, the long life, the lack of the lack of moving parts, etc. From your experience, is it panning out that way? I mean, these are not an electric vehicle that's running along the road, a relatively gentle duty cycle. These are engines that are going to be running at full power for takeoff, climb. There's going to be transients, very different environments on the ground and in the air. What is are they really going to deliver the maintenance cost savings that the industry thinks, or that those of us looking at electric aviation are told are there?
In a word, yes. But this gets back down to the requirements and your design team. So we understand the electric engine very well. It's less complex, less moving parts. And as long as it's kept within its, we'll say, proper operating environment when it comes to thermals and temperature, things like that, these things will last an extremely long time. So I have high confidence, and I think we can, just start to see other applications, other industries that have really picked up electric engines or electric motors, and seeing just how that plays out. So I have very high confidence that TBO for really anywhere in the aircraft industry is going to be dramatically reduced. And I think we mentioned already on this call, like some of these, we'll say incumbents are 50, 60, 70 years old in design. Of course, even if we'll give them the benefit of the doubt, if they went back and took all the technology that we know today and still came up with an internal combustion, application, it would be better TBO than what we're dealing with now. So really, this is a chance not only for us to leapfrog into a new technology, which is better by itself, but also really push the industry forward into where they should have already been if they had just continued to, we'll say, innovate.
So I have a question here, which is an interesting one. And it's, how does the current power-to-weight ratio of aviation electric powertrains compare with, well, it's turbofan engines, but really we should be saying turbine engines. And the interesting thing here is we don't compare apples and apples when we talk this. We talk about the power-to-weight ratio of a turbine engine, and we forget about the fuel system and the fuel. And then we talk about the power-to-weight ratio of an electric propulsion system, and we bundle everything in, right? The thermal management, the batteries, everything like that. So it's, but I mean, are we within sight of being able to develop a propulsion system, whatever you bound it, wherever you bound it, that is truly competitive with in terms of performance and with today's turbine engines?
Yeah, so maybe I'll also refer here to Jeff, but I think the answer is yes, we're within sight. Now we have a little bit longer, we'll say, horizon on these development cycles due to regulation, but we will surpass where we see the market today.
Jeff, I mean, you're aiming for really to take on, you know, like a 10,000-pound class turbofan, I suppose, you know, or an 8,000-pound shaft horsepower turboprop or something. When you get to your bigger engine, I mean, it's taking on you know, it's aiming not at a PT6, but something significantly larger. I mean, do you feel that the competitive performance is definitely on the cards?
Oh yeah, absolutely. I mean, there's no question on the electric propulsion side, the performance is there. You know, the power to weight ratio of these machines that are being developed by ourselves and others as part of, let's say, the RPE Ascend program, which is what we're part of. They're essentially apples to apples with jet engines. If you look at the overall system, of course, it's going to be heavier. You know, jet fuel is amazing at what it does, and whether it's a hydrogen fuel cell or batteries, you're going to have to take a trade-off. And so that's why the example I gave of the C-130, you're going to take a range limitation. You could have gone, you know, 1,500 miles, 2,000 miles. Now you're only going to go 600 miles. But the reality is that for so many of these applications, those short ranges are completely acceptable. You know, you look at, for example, within the narrow body market, 50% of the flights that the narrow body market is doing is flights shorter than 800 or 1,000 miles. And so what that gives you is an opportunity to create a class of airplanes for that market, which then, you know, opens up, you know, dramatic reductions in terms of noise, in terms of emissions, and in terms of costs as well.
So, George, we're running out of time here. I just want to come back to you and say, you're on the receiving end of all these promises. You're looking at the industry. They're telling you what they can do. Can you give me some idea of your level of confidence that what you want to do is going to be that the industry is going to supply you what you need?
Well, I have 100% confidence that electric engines is definitely a future for advanced air mobility and regional air mobility. In our case, we're looking at distances of up to 500 kilometers. So we're talking about unpressurized aircraft. We're talking about real advantages for electric aviation, and really just looking at the automotive industry, of which I personally was extremely skeptical 10 years ago, and look where we are today. I fully believe that in what Jeffrey and Paul are doing in terms of electric engines, it's inevitable for regional air mobility to move from piston engines, turboprop engines towards electric engines. I'm also very confident that we're not going to see batteries in quite near future sufficient enough for our size of aircraft. There might be some genius that comes up with new technologies, as mentioned yesterday, but I'm very confident. I'm very confident in that ZeroAvia can supply us with a fuel cell that works. The real challenges for all of us, and the real difficulties will come down to certification, and this is where we see real work to be done on industrial level, because even what Paul and Jeffrey mentioned about the TBOs of engines, we have to go to regulator and say, look, these engines can sustain 5,000 hours, 10,000 hours, and regulator has to confirm and agree to that and issue regulations that for the maintenance. So as an industry-wise and as aviation in general, from little guys that build in 2-seaters all the way to 100-seater aircraft, we need to work together with the regulators to make sure that these new technologies can be implemented as quickly as possible and safely, of course.
Thank you, George. Thank you to all of my panel. Thank you to ZeroAvia for inviting us, and hope you found the panel informative.
Thank you so much, everybody.